just give me what I'm asking for. Just convert basically my C code into machine code. Don't add anything extra into it. So this is all trial and error. None of this is documented anywhere. So I spent a fun afternoon, I'd compile, I would look at the listing, I'd look at the machine code that got generated. I tried to run it, it would blue screen, repeat, rinse, wash, repeat several times until I finally got it right. And another thing I wanted it to do was to make sure that the machine code that I generated was in the same order as the functions that existed in the source code file. So as you read the source code from beginning to end, the source code, the machine code gets generated in the same order as the functions in the source listing. And you can actually see that I was successfully able to do that by looking at this header file in my source code. What I did was I took the shellcode out and converted it into a C array so that I could play with it later on. So this code section in the file you create, in this executable you create, that's really what you're after. All that extra stuff that gets created, you don't need. All you want is that shellcode. So how do you find out where it is in the file? There's a tool called dumpbin, which is pretty standard, which will tell you, for each section, where that section is located as a raw physical offset in the file. And so that's how I did it. And then I went old school. I probably could have written a tool to do this, but I was in a hurry. I was too busy doing what I was doing, and I didn't want to take the time to stop. So I just used a hex editor and ripped the code out from, it started at offset 400. As you can see, there's some nulls that are padded in there, and I have a feeling it has something to do with alignment of sections or something to that effect. And because this code's position independent, you can pretty much ignore the leading nulls. That's what I did. So I ripped this code out with a hex editor. So when you're dealing with shellcode, especially in the kernel, one mistake can ruin your day. You will get a stop error, you will blue screen, and you'll sit quietly and watch your machine restart. Or if you're using a virtual machine, maybe you can save yourself a little bit of pain. It'll be a little quicker cycle back from blue screen. So one thing I did to kind of ease the pain of this process was I started off, normally you'd load the shellcode in somewhere and you'd modify the system to intercept the path of execution so it could execute your code. But I didn't want to I wanted to keep the modification of the system as small as possible, so I stuck this shellcode within a routine in a kernel mode driver that I'd loaded. Right, and so that kind of allowed me to safely manipulate stuff without having to modify, anything else. I just load my shellcode within the confines of my own kind of laboratory, which is this kernel mode driver. And this placeholder routine is nothing more than just a bunch of nulls, a bunch of no ops, right? And then so I load the shellcode into this placeholder routine, and then launch it as a system thread. And in that sense, I could kind of test things out before actually making the jump and actually, modifying the system and loading the shellcode in that way. But again, this is a little too conspicuous. You don't want to load a driver just to get just for the sake of, if your shellcode and the driver's, running at the same time, it's just a giveaway. So it's more like a training wheels kind of approach. So one way you could launch this code, if you wanted to launch a shellcode, was you could have a staging driver, which exists strictly to allocate memory somewhere in the kernel, maybe through the non-page pool or something like that. And then you could have an exploited user mode process, which through device I/O control takes the shellcode and loads it down into the space that you've allocated. Once you've done that, then the rest of it's just scaffolding. It can self-destruct and poof, vanish. Hopefully removing traces of itself that, of the staging driver and everything else you don't need anymore. So you have this shellcode that's loaded, right, that you've loaded. And in and of itself, it's pretty benign. It's just a bunch of bytes in memory. It's not scheduled for execution by the kernel because you didn't use the loader. You didn't register it through legitimate channels. It's just a bunch of bytes in memory. And it has no formal interface to the I/O manager, again, because it's not a driver, it's not anything else, it's just bytes in memory. So it's kind of swimming alone, with no connection to the rest of the system. Poor lonely shellcode. So how do we get it to execute? Well, we need to intercept an existing path of execution. And this kind of brings to light a misconception that I started off with when I started working with system software. I was under the notion that the kernel mode and user mode kind of ran independently of each other. In other words, it's like two software engineers who are in cubes next to each other. They kind of sit there and spin and doing their own thing. And every so often a joke or something will pass over the side of the cubes between the two guys. And so that's how I kind of saw how things, but it's probably more realistic to say that the execution context of a system is a bunch of paths, and they flow pretty naturally from user mode to kernel mode. And all you've got to do to get your shell code to execute is to intercept one of those paths. And so there are ways you can do that. You can modify, you can modify the system. You can call table hooking as one way to kind of intercept an execution path. There's detour patching. You can go for kind of a dynamic approach and manipulate callbacks. If you want to kind of do the walk before you can run approach, and I actually done this, and you start off by manipulating the system using table hooking. And when you feel comfortable with that, you move on and you switch it over to a detour patch. And once you feel like you can do that comfortably, then you move on to patching dynamic stuff, which makes it harder for people to detect that you're there and you're moving around. Okay, so we looked at implementing shellcode. How about implementing the heartbeat, which is what the primary rootkit will emit, and this backup rootkit will detect. There are different ways to do a heartbeat. You could use the existing TCP/IP stack, which means you just be using standard APIs to create network traffic. And there's a couple different APIs at the kernel level. You can none of them are painless, but it's still easier than rolling your own stack or talking directly to the network card. You could, if you wanted to, roll your own TCP/IP stack, which would be a lot more work and be less conspicuous, because the connection that you create then with that new stack isn't registered by the old stack, and basically all the system mechanisms that are there that use that stack. So if you were sitting in front of the console, you wouldn't see the connection, because all the existing equipment in the operating system is assuming that you're using the current legitimate stack, and you're not. And it also allows you to bypass filtering mechanisms, which are also built upon the existing TCP/IP stack. So you build your own, you can bypass all that. If you really want to go full geek, you could probably talk directly to the hardware. But that's a full-time job in and of itself. So there are probably people that's their job, is doing that kind of code. So like I said, the latter two offer better concealment from the standpoint of someone sitting at the console. If you're running TCP view or netstat, you won't see any of this. If you've rolled your own stack or you're talking directly to the hardware, you won't see any of that if you're using these tools. And you won't have to worry about any firewall rules, because you're not using the stack which is subject to those rules. But there are problems with this approach. And it comes down to that Harlan Carvey's observation that the absence of an artifact is itself often an artifact. For example, if you have an enlightened or maybe paranoid forensic person who's decided, I'm going to start capturing all the network data that's coming off of this compromised machine, and so they're doing a full content data capture, they might see this traffic, and they're going to go back to the machine, and they're going to look, and they're not going to see it. So they're going to say, my God, I don't see this connection, this HTTPS connection, or I don't see this ICMP traffic, or whatever. This isn't showing up from the console, but yet I'm seeing it over the network. So this discrepancy exists, and in a sense, it serves as a hallmark, that something's wrong. That will raise the flag. The whole idea of a rootkit is to make the person at the machine, or who's doing the investigation think, there's nothing wrong with this machine. There's nothing here. Go back. Go away. There's nothing here. And if they see something like this, the jig is up, because now something's wrong. There's an aberration. So we have to make concessions. We want to be stealthy, but at the same point, we don't want to be so stealthy that we become conspicuous. So the solution I decided to go with was protocol tunneling, right?